So the first thing we're going to do is talk about what is an inverse. This is from pre-cal. This is pre-cal world, before we got to calculus. An inverse function basically undoes one function. So you can think of like addition and subtraction. Those are inverses of each other. Sine and inverse sine, right? You know, when you do those. Multiplication and division, inverses of each other. And so inverse functions are basically the same thing. We did this, like I said, in the pre-cal world. You'll notice this little notation here, f of g of x, that is composition. When you do the composition of inverse functions, you will always get x, or they are not inverse functions of each other. That's just how it works. And you can do it either direction, f of g or g of f. Notation. For notation, we have this little -1, which, by the way, on your calculators, you'll see sine to the -1. That doesn't mean 1 over sine. That means the inverse function of sine. Same thing here. When you see f to the -1, it doesn't mean 1 over it. It means the inverse of f, or f inverse. This first example says, show that functions are inverses of each other. Well, the way we show that is we take the composite. Either direction, it doesn't matter which way. So if I wanted to show that these are inverses, I would just say, well, f of g of x, and see what that does. Remember, when I do f of g, I take all of g and I put it into f. So f is 2x cubed minus 1. So I'm going to say 2, and instead of x cubed, I'm going to put my g function there. So I'm going to say cubed root of x plus 1 over 2 cubed minus 1. All right, and then I'm just going to simplify it. At this point, I'm just algebraically simplifying it. So a cubed root and a cubed will cancel each other out. And I'm left with 2 times x plus 1 over 2 minus 1. My 2's will cancel. And I am left with x plus 1 minus 1. The x's will cancel, and I'm left with x. That's what I'm looking for. Yes, those are inverses of each other. The graph of f contains the point AB if and only if the graph of f inverse contains the point BA. So if you'll remember, and this was way back when we first started talking about functions. Functions are one-to-one, which we're about to talk about. And then inverses actually just flip your x and y's. So if you'll recall word problems that we did, like for example, you get paid $15 per hour and your total for the week was $45. That means you worked 3 hours, right? Or if you did the inverse, the input there was hours and the output was what you made. The inverse function would flip that. The input would be what you made and the output would be the number of hours. That's what happens with inverse functions. And so your input and output, or your x and y values, just flip-flop. And that's all this says. And you'll notice the graph here. This is a function. This is the original function here, right here. And the inverse actually flips across the line y equals x. And so you have this flipping across the line y equals x, and all of your x and y's then flip. That's what happens when you reflect across that line. And so that's just a reminder that this is actually a theorem here. This is a proven theorem that if you have a function and its inverses, those x and y's will flip-flop. That's what that's saying. Which leads to the next one. Is the inverse a function? So it can have an inverse, but it doesn't necessarily mean the inverse is a function. A function has an inverse function if and only if it is one-to-one. It has to be one-to-one both ways to be an inverse function. I'll give you an example, a parabola. If you have a parabola, right, and we all know, hopefully we all know what a parabola looks like, right? You have this guy right here, okay, parabola. If you were to flip him across this particular line here, would he be a function? Not necessarily, because I'm pretty sure you're going to cross over yourself, okay? And so when you have certain functions, you can find an inverse, but the inverse is not a function because all of a sudden the inverse is not one-to-one, right? And so that's all this is saying here. You can find the inverse of these. Is the inverse then a one-to-one relationship? And that's what they're asking here. Which of the functions has an inverse function? And they give you the graph over to the left. The first one is 1 to 1 and the second one isn't. So let's look at these graphs. So this is the graph of the first guy. The way you can do it is similar to how we tested function. One way that we tested is it a function given the graph is the vertical line test, right? And so vertical line test would tell us, hey, if I draw a vertical line anywhere on here and cross it only once, it's a function. So to find out if the inverse is a function, you can use a horizontal line. So I can say, well, I know this is a function. Is the inverse a function? Well, draw horizontal lines. Can you draw horizontal lines and only cross it once? Yes. Then when you flip it, those will be the vertical lines and they're only crossing it once, right? And so this guy will have an inverse function. The inverse of this guy will be a function because horizontal lines become the vertical if you were to flip it sideways, right? And so you can use horizontal lines on your original function and say, yeah, if I flip this guy sideways, he would be a function as well. All right. So then let's look at the next one, this x cubed minus x plus 1. They look very similar, but they are different. This is the graph of the second function. Vertical line test, yes, the original guy is a function, but when I do a horizontal line test, we have a problem, right? If I flip him, you can see that a vertical line is going to go through it more than once. And so that is not a function. So it is not a one-to-one relationship when you flip it. And so that tells you that the inverse is not a function there. We do not have an inverse function that exists. So the first thing is determine whether the function has an inverse. Does it have an inverse? Solve for it, which means when we solve for it, you switch x and y and then solve for y, which is all it's telling you in number 3. Define the domain and range so you can double check and make sure you don't have any domain and range issues, and verify that if you were to take the composite that you do have an x. So you can actually check your work. You can solve for the inverse, then you can do the composite and say, did I get an x when I did the composite? Yes, I did. I did it correctly. So if I were to graph this, they show that to you on the left, you're going to get a graph that is kind of like this, right? On the coordinate plane there, it actually starts at 0. And then if I were to flip that across, we're still in a 1-to-1. So we're good as far as does it have an inverse. So then I'm going to switch my x and y and solve for y. Remember, f of x is just y, right? So if I were to switch these, it would be x equals the square root of 2y minus 3. And then to get rid of my root, what do? Well, I square both sides. So I'm going to square this side, square that side. X squared equals 2y minus 3. Add your 3 over and divide by your 2. So y equals x squared plus 3 over 2. You do want to rewrite this notation to be correct. It's not y. Technically, it was written in f of x. So we're going to say f negative 1x equals x squared plus 3 over 2. So, all right, so checking it. Check it either way. It doesn't matter. You can plug this into the root or you can plug the root into this. I would actually plug the root into that. It's just easier. So I'm going to plug this into that function. Instead of x squared, I'm going to write square root of 2x minus 3 squared. So x squared plus 3 over 2. All right. When I do that, my square and my square root cancel. So I have 2x minus 3 plus 3 over 2. My 3's cancel. I have 2x over 2, which is x. Yes, I did that correctly. Those are inverses. So from theorem 5.7, which we're trying to figure out is an inverse function, sine of x is not a one-to-one relationship naturally if you just do over the entire domain. All right. If you were to draw a horizontal line across sine, it's a wave, right? And you're going to cross it. However, in this case, they gave me some parameters from negative pi over 2 to positive pi over 2. For just that domain that they restricted me, it is one-to-one. right? And so if I were to do just the regular old sine graph, remember we go up, back down, and back up, right? That is not 1-to-1. But when I do it at positive pi over 2 and negative pi over 2, so negative pi over 2 is over here. If I do that from negative pi over 2 to positive pi over 2, when I restrict the domain, yes, that part is a 1-to-1 relationship. And so you can have stipulations where they restrict it, and then it is 1-to-1 at that point. If they did not give me any restrictions, if it was over from negative infinity to positive infinity, we don't have a 1-to-1 relationship for sine, it's a wave. But if they restrict it like that, then you can see, yeah, that actually would be okay within those parameters. Within those parameters, I could possibly work with the inverse function there. But outside of those parameters, I'm going to have a problem. It's not going to be a function. It's going to be undefined. All right, theorem 5.8, it says continuity and differentiability. F is a function whose domain is in an interval I. If F has an inverse function, then the following statements are true. F is continuous on its domain, then the inverse is also continuous. If it's increasing, then the inverse is increasing. If it's decreasing, then the inverse is decreasing. If it's differentiable, and the derivative does not equal 0, then the inverse is differentiable at C. All right? Let's look at theorem 5.9. Right below that, we have 5.9. Let f be a function that is differentiable so we can get the derivative on the interval. If f has an inverse function, and we'll call it g, then g is also differentiable at any x for which the derivative of g does not equal 0. And this is how you define it. So if I have my original function and I know it has an inverse, how do I get the derivative of my inverse? That's what this is saying. The derivative of the inverse is always going to be 1 over the derivative of the function composite with the inverse, okay? The derivative of the function composite with the inverse. And this does have a stipulation. This cannot be 0 because it's in the denominator, so obviously we can't divide by 0. So how do we actually evaluate it? Let's look at example 5. Can I do it? There we go. All right, so value of f -1, we're talking about the inverse. So this is actually the y value. What is the x value? There's a couple ways to do this. You can set it equal to 3, which is kind of a pain. They do graph it, or you can find the inverse and then plug in a 3, right? So if I need to figure out what my x is and they've told me the inverse piece when x is 3, I need to find the inverse to figure out the input because they switch. So how do I find this inverse? It's a hideous one, by the way. So we're just going to use their graph. If you look at the graph, we can see how they work. I'm going to plop the graph. So if we look at the graph, my original function is here, right? My inverse is here. My original function is here. My inverse is here. They are asking for 2 different values. They're saying, what's the value right here when x is 3? Well, when x is 3 on my inverse, y is 2. When x is 3 on my inverse, y is 2. All right? We know that because we can see that when y is 3, x is 2, and they flip-flop. And you can see that happening here. All right? So f of x equals 3 when x is 2. So then the inverse at 3 when I input is 2. They just switch places. They just switch places. And so this first thing is asking, well, what happens when you input 3 into the inverse? If I were to say f of -1 of 3, my inverse, this is my output because it has switched. So the answer there is 2. Now they want to know, how then do I find the inverse? I mean, the derivative of the inverse, the derivative of the inverse. And we're going to go back to the derivative of the inverse. We're going to say that is 1 over this guy right here. 1 over that. So here we go. We say, well, g of x, that is my inverse, and I'm talking about at the point 3. So we're going to say 1 over f inverse of, or f derivative of g of 3. What is g of 3? We just answered that question. G is my inverse. G of 3 is 2. So now I'm going to say, well, I need to do f derivative of 2. F derivative of 2. How do I find what happens when I plug 2 into my derivative? Well, I probably need to find my derivative, right? We know how to find derivative. We're going to take my original function and find the derivative. Multiply by 3, that's 3 over 4. X squared plus 1, and then my negative 1 drops off, right? That is my inverse. That is my derivative, correct? Good? They're asking what happens when I plug a 2 into that. Plug a 2 in. So we're going to say 1 over, we're going to take this and plug a 2 in. 3/4 2 squared plus 1. So we have 1 over 3/4 times 4 plus 1. 3/4 times 4 is just 3. 3 plus 1 is 4. It's 1 over 4. That is actually what happens with the derivative. So derivative of my inverse at a function is going to equal this guy. So the derivative of the inverse, in this case, at 3 is going to equal 1/4. So all we did was we used this formula. If you know this, then you know the x and y's switch. They switch for the inverse. And so if you know your x and y values here, you can flip-flop them for the inverse. And that's how you can find out what my x and y values are. You can find it in one spot and flip-flop it for the other. So if you have the inverse, you can plug it in and flip-flop it. That'll be your x and y. If you have the original function, you can switch your x and y, and that will be your inverse as x and y. That's what you're doing. You're just going back and forth.